Okay, my name is Ralf Metzler from the University of Potsdam, and I'm kind of the diatribe of Thomas yesterday. I'm a physicist, and I will be very loose in some of the definitions and things I'm using. But as yesterday, please interrupt me. I have too much material as always. So rather than boring you with all of it, let's have a discussion on the way. And you ask me whenever something is not clear. Okay, this, by the way, is a painting by Turner of Carroll in Cambridge, who also spent some time here, obviously. And when we talk about diffusion, that was alluded to by Thomas yesterday already, that we have two kinds of approaches. And one approach, of course, we always associate in Western literature with Einstein. But of course, I have a lot of Polish friends. We should not forget Smolkowski in this endeavor. And then essentially they published very similar papers, but Einstein, he had more important things to do, so he went to relativity and everything. Whereas Smolkowski really kept with diffusion and had early descriptions of diffusion-limited reactions and so on. And the third guy is barely known nowadays. This is William Sutherland, who actually wrote more or less the same results in 1905 as Einstein, but his paper just got forgotten. Nowadays, when you want to be politically correct, you call the Einstein relation the Einstein-Smolkowski-Sutherland relation. It's a bit long, but you know. And then, of course, we have Paul Langevin, who came up with the concept of fluctuating forces that we still use in statistical physics of non-equilibrium systems until now. And this is the description I will, I guess, mostly use in my talk, going back to the stochastic equation. And it's one of those fields where actually theory came and then the big experiments were realized. That's one beautiful thing. And when we generalize models, we try to publish them, and then there's referees who say, oh yes, but tell me an experiment that shows this. An answer could be, you know, sometimes theory can inspire experiments, or what we actually look at. So here, these were results by Jean Perrin, who got the Nobel Prize in 1926 for his work on determining Avogadro's number. And one of his biggest, most successful approaches was using diffusive colloidal particles, essentially, that he could just see in his light microscope, and he had these trajectories, and then he was evaluating them on an ensemble level because the trajectories were very short, and then he more or less fitted a Gaussian distribution for this time step that he was evaluating, and then used the Einstein-Smolkowski-Sutherland relation to extract from all the other known quantities Avogadro's number. And this was his results, you know, we're talking 1908, and this was a big step in establishing atomic theory of matter. Actually, he summarized his results in a book called Les Atomes. Very few years later, it was this guy, very unknown scientist from University of Uppsala in northern Sweden, Ivar Nordlund, and he was very good at photography, so he wants to get rid of these ensemble averages, because the particles were not exactly the same. They couldn't reproduce them exactly. So he invented a tool where he had a moving photographic plate, and then he could actually follow a slowly sedimenting mercury droplet in this stroboscopic image. So time goes to the right here, you see deterministic sedimentation, and on top of it, you see an illusion of this particle as a time series. This was the first single particle tracking experiment of high quality. And then he could evaluate individual experiments, extract Avogadro's number from them, and then average over several of these experiments. And you see, I mean, there was a huge gain in accuracy. And this kicked off a whole race. And I could be talking about this for the rest of the seminar, but I also want to emphasize that all these theories of diffusion, they're not only for colloidal particles. Of course, we have a diffusion coefficient that gives us a time scale that we can adjust. We can describe all kinds of processes. And actually, Louis Bachelier in 1900 already anticipated many results that Einstein published later, but his thesis essentially got forgotten because he was a student of mathematics and did financial market modeling. I mean, he almost didn't get his degree for that. But, you know, the idea to use it for such kind of systems was already there. Carl Pearson, very famous statistician, he invented the random walk to describe how mosquitoes spread in a pristine area. Elliot Montroll was involved in the Manhattan Project, described chain reaction of neutrons by random walks. And of course, Smoluchowski, as I mentioned already, used it for reactions, molecular reactions. So in my group, we are working a lot on anomalous diffusion when the mean square displacement typically goes like a power law. And I will change notation a few times. So alpha is the anomalous diffusion exponent, and it's related to this Hurst exponent that we'll be using just by a factor of 1/2. And then, you know, we can ask all kinds of questions. I mean, these are experiments by Yuval Garini where they can follow the end parts of the chromosomes in the nucleus of a living cell. Or this was a paper together with Diego Prof, who can measure, I'll show you the experiments, little proteins in membranes of living cells. And we try to make sense of all of these questions. For instance, we look, how is the process? How is it characterized? Is it non-Gaussian? Is it ergodic? So that's one of the questions also coming up in many applied fields by now. Can I infer the ensemble average from a long time average? And it's not always possible, and I'll show you examples. And of course, aging non-stationarity is involved there as well. So I have two slides at first where I just show complicated systems. And in some cases, the complicated system can be described in very simple physical terms. So this is the first example. This is an old work together with Ilpo Vahtolainen in Helsinki. And we were looking at model membranes. So these are coarse-grained simulations of model membranes. So the membrane is spanned by small lipid molecules. They're the fine grains here. And then we decorate them with loads of proteins. They naturally occur in membranes. So we just put a lot of them. And all of a sudden, fundamental laws that people use in membrane physics change. So for instance, the diffusion coefficient of a single molecule follows this logarithmic 1/radius law, whereas in the crowded membrane, this changes to a much more pronounced 1/r. And the 1/r, if you want, you can exactly model, not absolutely the diffusion coefficient you have to normalize, but once you do this, you can understand exactly the dynamics of this complicated system by hard disks of the appropriate radii. So it actually becomes a question of what's the likelihood that they can pass each other, which of course is proportional to the radius. So in this system, we see normal diffusion, and we can understand these laws, at least a big part of what you see dynamically in terms of simple ideas. I show you another example. These are simulations together with Mike Finnis from Imperial, where they have two glass surfaces, and in between, they model a very innocent drug molecule. It's more or less stiff, it's a stiff rod, but it interacts with the silica surfaces, and the motion we observe is extremely rich. I will not go into details, but we see non-ergodic behavior, time and ensemble average is strikingly different. We see anti-correlations, we come back to in a moment, of the velocity-velocity correlator. And we see non-Gaussian diffusion, we even see power law waiting times. And I have no clue where they're from. It's such a simple system. And of course, we try to follow up and extract where it's from by changing parameters and solvent. But just an example where an innocent-looking system has an extremely complex behavior.
I mean, is that really innocent looking?
Oh, yes, it's absolutely innocent-looking. So maybe it's because of the yellow stuff here that it looks so dangerous. Okay, so now let me come to the first example that I have, and then I will move towards the correlated processes. This is a measurement that's already quite some years old by Diego Krapf's group, and they follow potassium channels. These are just proteins, big proteins, moving in the membrane of a living cell. And what they see, these are very long trajectories. This is 1 micron, and they can measure them for several hundreds of seconds. And this is a sample trajectory. And what happens there, these particles, they move quite happily, and then they get stuck. There's an interaction with a biochemical center, and then they're released again and move happily. So this is intermittent motion, and they can actually extract an asymptotic power law waiting time distribution. And once we have such distributions, of course, in a finite system, they will never go forever. But the observations I will show you are within the time of the experiment. It's as if the process is described like this. So we have these power law waiting time densities. When alpha is between 0 and 1, the characteristic time is diverging at infinity. Okay? And of course, then a time average of an observable, any observable, here, for instance, the mean square displacement, stays a random quantity. That's what you see here. These are experiments on the motion of these proteins as a function of time. You have a log, and you see that for something like 20 realizations, the amplitude of your time average mean square displacement varies by, I don't know, 1.5 orders of magnitude. And this was known at that time from experiments on blinking quantum dots, which also lack a fixed time scale. And it's not the bad student who's doing the experiment. It's really the physics of the system. They also see that when they take the mean square displacement, the time average, and they plot it as a function of the observation time, they see aging. So on average, the mobility is a decreasing power law in time, in measurement. And this is clear when you have one of these power law waiting times and you draw realizations more and more. On average, you will get longer and longer waiting time. So on average, your particle is slowing down, causing the subdiffusion. It's one way of causing subdiffusion, which means slower than normal diffusion. And the alpha here is the same as the T to the alpha in the mean square displacement I showed. So this translates. And for these systems, you can show that the time average mean square displacement scales like the lag time, that's your experimental window that you slide along the time series, divided by the measurement. The ensemble average has a delta to the alpha. Here you can see immediately, this is anomalous diffusive. If you were only looking at the time average, you could confuse it with Brownian motion, with normal diffusion. You would have to actually look at the scaling in the measurement time to see the anomaly. So this is one of those examples where things can already get, you need to know a bit more about the system. You need to probe more than this one quantity. And also, just an aside, for this kind of process, you always get a non-Gaussian displacement distribution. Now, let me go back one step, look at even simpler systems. Again, innocent systems that show some very strange behavior. So this is called Brownian yet non-Gaussian diffusion. Actually, across the whole here, Ray Goldstein is also, the experimentalist, is also working on statistics like this. So look at this. This is, and this is work by Steve Granick's group. So this is a nanorod, and you have colloidal particles moving on the nanorod. Looks very innocent. What they see is mean square displacement has a slope of 1, different realizations, all nice. And then they looked at the displacement density. So for short observation times, it's a perfect Laplace distribution, exponential tails. This is log versus limit. For longer times, still exponential tails. And then there's a crossover time, very long times, they see a crossover to a Gauss. They have other experiments like a bait in an actin mesh where they don't see a crossover. It's just the measurement time doesn't show. Again, linear slope of the mean square displacement. And here always an exponential. There's loads of other experiments. For instance, here there's one with mini worms that show this. And of course, in biology, when people want to show an exponential, they don't plot it log versus ln. They use ln, and then this looks like an exponential, whatever. So it's the same phenomenon. And how can we kind of understand there's many different approaches? I want to show you one very simplistic one, and it's based on a heterogeneous environment where our diffusion coefficient fluctuates as a function of time. You can understand it, for instance, from systems like this, where you have membranes that phase separate, and then you have a tracer particle that can move on this surface, but it has a different diffusivity in these. Is it red and blue? Different diffusivities on the red versus the blue patch. And then, you know, when you follow the particle, it crosses the boundaries and it has a larger or a smaller diffusivity as a function of time. something like in this sketch. Of course, here we have a quenched environment, so that's a little bit problematic. I can show you an even more natural realization.
So why problematic?
Because each time you come back to the same point, you get correlations in your motion. So you get some correlations here that I neglect in this kind of approach. Every quenched environment are difficult. There's a beautiful new work by Universität on archive yesterday. So there's only numerical work so far in that direction. And of course, in 3 dimensions, it's less severe because in 3 dimensions, return probability is very small. But in 1 and 2 dimensions, you get some corrections. Due to
When you're looking at what quantity you think giving you problems?
well, for instance, if you want to infer the probability density. Of microphone?
Is it for?
Could be mine. Okay. House is burning down. Anyway, so this is a cleaner system in that sense. So here we have simulations of a protein, and it's a protein that can shapeshift. So it's not a protein. It's making it sound. It's a protein that can shapeshift. So as a function of time, it can assume all kinds of different configurations because it has a very shallow energy landscape. So it can jump from one little minimum to another. So it can be very compact or very extended. And of course, this influences the radius of gyration of the hydrodynamic radius. And we showed that the radius of gyration, the average extension, fluctuates very vividly as function of time. Look at the gray lines. I hope you can see them. Here we have an example where it's extremely extended, so that would be this configuration. And the time local diffusivity is exactly going the opposite way. So when it's very extended, it's very slow. And you see, we create a stochastic diffusivity. Another example from a paper by Denis Krevenko, where he has kind of a hydrogel, and the hydrogel is fluffy, it's breathing. But when the particle is right now in an area that's very dense, of course, it's slower, and then it goes into an area that's looser, that offers a lot of freedom, then it becomes more mobile, and as a function of time, we have these stochastic diffusivity. And if we insert this into a model, this was actually first done by my old colleague Gary Slater in Ottawa, and he also created the word diffusivity for this. And then with my friends, especially Alexei Chichkin, whose old style Moscow school, he wanted to have an analytically solvable model, which we managed. So we came up with this minimal model for this process. So we have a Langevin equation. Now we see it for the first time. This is white Gaussian noise, but we modulate with a time-dependent noise strength, if you want, the diffusion coefficient. We want it to be positive, so that's why we map it onto some other quantity squared. And this quantity y follows an Ornstein-Uhlenbeck process. We wanted something that is stationary. So we also start with a equilibrium distribution for this y. And then we plug in this y into the leading differential Langevin equation. The first funny thing is, if you start with equilibrium conditions for the y, your mean square displacement is linear everywhere. I divided by t here, so you see it's perfectly horizontal. The PDF, of course, in every simulation, in every single realization, you start with one given value taken out from the equilibrium distribution. And then for these single realizations, what we get is actually short time exponential tails. We get a little bit of power law corrections at the center. So these are kind of what were these Bessel K solutions. And then at long enough times, and the time scale where it crosses over is given by this time scale of the Ornstein-Uhlenbeck, we cross over to a Gaussian. That's a very primitive, very simple model. And we can see the kurtosis exactly shows this crossover. We also look at non-equilibrium conditions, more general stuff. But this is a very simple picture that I want to come back to. And the beauty about this, there were many, many different formulations of this model. A little bit different here, a little bit different here, but the whole phenomenology is the same. It's a very robust one. This is what I like a lot of this. You will see that when we go to correlations, this is gone. Now, this is a paper. Yes.
Question. The previous slide, what is happening with the diffusion asymptotic?
It means the displacement stays linear with the same coefficient at all times,
Right.
which is given by kind of the average over the diffusivities in this harmonic potential. And here you can see that at long times, this Gaussian, the width is given in terms of this effective diffusivity. Yeah, it should have said that, thanks. Anyway, so now I'm flashing up some results of a paper, including our great chairman, Ran, and look at this blue line. So I want to show you here that was a paper where we tried to use some observables that go back to Maru. And there's 3 scaling exponents. I'm always losing the names there, they're so complicated. One was Joseph exponent, this was the Noach exponent, this is the Moses exponent. I mean, Prof liked, yeah. He liked a good joke, actually. And they characterize correlations in the motion, they characterize whether you have extreme events in the statistic, and they look at non-stationarity. So look at these correlations. So these correspond to motions that are long-range correlate in time, where you have long correlations in the displacements or the velocity, if you want. And this ranges from single molecules over colloids to ants, and then we have all kinds of birds. Here you see, for instance, the movement of a vulture in Israel, Sinai, the Red Sea. And all those blue ones where the value differs from 1/2, these are long-range correlated processes. So I was amazed to see it in all these systems coming up. And this is why we also started working a bit more on these correlations. So that's, yes.
Is the value of tau before in the model?
No, no. This is nothing to do with tau. This is to do with this Hurst exponent. So this is essentially here an exponent that you would have in the displacement correlate. So that would be the long time thing. When it's 1/2, this exponent, I mean, there's some 2 minus this exponent or something. When it's 1/2, it's uncorrelated. And then you can have positive correlations or negative correlations. I'll define them on the next thing. So I want to use this fractional Brownian motion as a model for these long-range correlations. You can understand where they come from in the model system. For instance, look at a polymer chain or a cartoon for a polymer chain. We have beads with a given mass, and they're connected by harmonic string. One can actually solve this, and when you integrate out the motion of all but one bead of interest, you get memory kernels. This is the work by Zwanzig and Kubo and whatnot. And what you see is if you give this one a kick to the right, you strain this spring. So immediately it feels a restoring force, and of course the opposite to the left side. And then this disturbance is moving up the chain and coming back. And this is what creates power law correlations in that process. Of course, this here would be in a finite temperature, and it's given by a bit more complicated description. I want to consider fractional Brownian motion where my noise is external, and this is what I can do for non-equilibrium systems or open systems in Freeman-Dulwich sense. For instance, biological cells, they are not equilibrium. There's lots of non-equilibrium animals, weather, finance. And the process is defined by this. So we have a Gaussian equation, but now the noise is correlated. So the first result is my mean square displacement has this form, so it's this power law form, and the noise correlator looks like this. So asymptotically, it has exactly this power law behavior. And now see when h changes value, h can be between 0 and 1. You see when h is 1, this is ballistic motion. When h is 1/2, it's Brownian motion. And when it's smaller than this, it's active. Now, when h is smaller than 1/2, you see that this thing here is getting negative. These are anti-correlations. That's exactly the motion we have here. You move in one way, the next step will be the opposite direction. Good. And then one can calculate the displacement correlator exactly for these processes. And now I'm lost with colors again. So when H is 1/2, you see the correlator goes down to 0 immediately, as you would expect. This is the bin time, and then stays beautiful. Subdiffusion, these two examples here, you see that it goes to these negative values and then recovers, and the recovery is actually a power law recovery, very slow. And for superdiffusion, for positively correlated motion, when H is larger than 1/2, you get correlators like this. Okay, so that's what this process is giving. I have one example here. This is from what we call viscoelastic systems. This is in worm-like micellar solution, work with my old friend Lene Oddershede from Copenhagen. This is an example from Matthias Weiss, and you can see these negative correlations. You also have an experimental example from Matthias where it's normal Brownian motion, where you don't see these correlations. So it goes down and settles at 0 immediately. One little caveat. It's not enough to know this correlate. This is an example from the motion of a bead in a critical percolation cluster. You can imagine percolation cluster particle gets stuck in a side branch. It can't go any further, so it has to return. So this is causing you negative correlations, but it's even worse. These are the symbols are simulations results. The full line is the model of fractional Brownian motion. So just by knowing the correlator, you wouldn't be able to tell. You need to know more. You need to have other observables to look at. Anyway, I also want to show you, back now to fractional Brownian motion, to our long-range correlations. I show you one example for positive correlation. So this is an experimental system, very complicated cell. It's an amoeba cell, and I don't show films, but if you look at the microscopic image, you can see the whole thing is swirling around. There's a lot of activity in here. And when you look at the scaling exponent, when you don't treat the cell untreated, you have an exponent alpha that's very, very high. So this is almost ballistic motion. And you get this kind of correlations, positive correlations.
So you said it twirls around. So
yes.
So what doesn't move? So this is the alpha related to what?
This is when you should have said that when you follow one of these little vacuoles inside the cell. Oh, sorry. Yeah, most important information. So then they follow these little particles and they see these positive correlations. And then these are biology affine people. They use all kinds of poisons, and then they kill the motion of, or the action of the motor proteins in the cell. All of a sudden it's stuck, almost completely stuck. And you see the alpha is getting to values, I think the average is 0.2. Very subdiffusive, and then the correlator looks like this, as we expected for subdiffusion. And these cells are really bad. I mean, they survive. They survive all the poison. After some time, they start moving happily again. And this is very difficult to see here, but after half an hour, positive correlations start coming back. And so on.
So the spiking that you see negative there.
Yes.
So why is it so spiky?
Oh, it's just because I show you a lot of stuff over here. If I were cutting off here, the spike would be less pronounced. I mean, look at here, for instance. Depends, of course, also on the value of the alpha. I show you some other examples afterwards, but it's typically you really have a very spiky behavior. Good. That's what I wanted to say. Yes. I quickly jump across this. I just want to say that one can use not only mean square displacements, but also single trajectory versions of power spectra to actually address this kind of motion. And it has very, very interesting properties. It's more stable than the mean square displacement. And you can, for instance, use it to say whether you have a sub, super, or normal diffusive system, just by looking at the coefficient of variation of the fluctuations of the power spectrum. But let me skip this quickly. I want to make one point, and this is that we're also trying to see what is the influence of measurement noise. So each time we have a trajectory that's measured, we want to take it and evaluate it. There is noise in the system. There is positional noise, that's called static noise, because you can never resolve exactly where your particle is, especially when you use low photon statistics for these super resolution imaging. But then there's also a dynamic error, and this comes from the fact that you have a finite exposure time. And during this finite exposure time, the particle is moving. So you get kind of an average over the position. And these are things that we try to include in the analysis. And for instance, with this power spectrum, we saw that this is quite robust towards these errors. Now, let's get back to a physical system. And this is again simulations I did with my friends in Helsinki. And these are very innocent systems. So I trust now I want to show you, starting from a simple model, making it more complicated, and we get some effects. So these are three examples of very simple model membranes. These are lipid bilayers. Here you see these are very floppy objects. So they have a head group, and then they have two tails. These tails are hydrophobic. So when you throw them in water, they self-assemble in a bilayer. And there's essentially, you don't see any water molecule in between. This is what I call the party phase. This is at room temperature. These are happy molecules. You already see they become stiff when you add cholesterol molecules. I think they are orange in there. These are cholesterol molecules. They make it more stiff. Or you can quench the temperature. It goes through a phase transition. It becomes even more pronounced, so much less energy. In all these cases, we show that looking at the displacement correlator, it's exactly this fractional Brownian motion stuff. And here you see again one of these very spiky results. It just has different alphas. But these are also systems where you get crossovers. It doesn't stay anomalous for it. It actually stays anomalous for 10 nanoseconds. This is completely irrelevant for anything macroscopic, for anything biological. But what we showed is, and it actually in some cases it crosses over to normal diffusion, and in some cases it crosses over to another anomalous diffusion just with a larger scaling exponent. And then we introduced tempering, a cutoff in my power law correlations, and you see results, simulations versus the analytical predictions. And what I don't understand is why the crossover behavior is so nicely reproduced. I don't have a handle for this. It just comes out so nicely. I don't complain, but I don't know why it works. I know that it should have the scaling here, it should have the scaling there. But so what we have a handle for is in introducing different kinds of cutoffs for the power law correlation, which you would expect in any finite system to happen. Good. Now let's see what happens when we go, and I should also say everything here is Gauss. This is beautiful fractional Brownian motion in that stuff. Now we add crowding. So these are proteins, and you see they're big chunky particles compared to these speckles. That's now a view from top. These are the lipid molecules, and these are those proteins. And you can already anticipate, of course, these guys are very slow. They move very slowly. So if you're trapped as a lipid in between there, you have a low mobility. And you get a mix-up of the mobility. But then when you look at what is the displacement distribution, you see that it's, here I plot the minus log of 1 minus the cumulative. Very odd way of plotting it, but it gives me the power law behavior in the exponential. And you see it's perfectly Gaussian for this dilute case. Once we go to the crowded case, we get scaling exponents here that are clearly not Gaussian. But it's also not exponential, somewhere in between. And we have simulations, so we can look at the system more closely. And this is the dilute system. So we look at individual time traces, we extract the local diffusivity from there. And you see these are quite stationary processes, and the distribution of apparent diffusivity is very good. Once we go to this crowded case, you see the distribution becomes very wide. I would not dare to claim that it's bimodal. My postdoc was very adamant that it's bimodal, whatever, it's broad. And you see clear intermittent behavior in those traces. And you also see that when you then look at individual lipids here, they all on top of each other for the time average mean square displacement, very homogeneous. And here you see in those crowded cases, you get a lot of heterogeneous. And we can actually see again, in a very simple geometric model, we can see a lot of this behavior. So this would be a two-dimensional hardcore gas, where you have mobile particles in here, then you have these obstacles where the particle has to squeeze through these little holes. Then the mobility is shrinking, and you get very similar behavior. Yes.
So you showed us that you get an anomalous diffusion if the size of the diffusing particle is bigger than the size of the solute particle. I guess that's the limit you're in here.
Yeah.
But I mean, I guess I can shrink those down to, and as they approach the solute particle, you've simply got a two-dimensional fluid.
Is happy ever after, yes.
And then it must be diffusive,
Yes.
I guess.
Well, you do have until these 10 nanoseconds. This is
right,
anomalous,
okay. But the exponent would be 2. So
it's first 2, then it gets subdiffusive, and then it gets normal diffuse.
right. So at late times it would be diffusive.
Absolutely.
So does that mean there's a critical size or something where you start the exponent changes?
Is a tricky question because people still don't even understand this crossover time, where it's from. I would guess so. I would guess there's a critical size. But don't forget that these are quite, complicated kinds of molecules. So I'm not 100% sure. For instance, people have an argument that they say this crossover at 10 nanoseconds. This is a time scale when more or less 2 of these lipids change position with each other. Forget about the initial condition. But in this case, the motion is much, much slower. Here you have a scaling exponent of 0.16. So it should take much longer until they change positions, but the crossover time is exactly the same. So it's a bit tricky to say. This is nothing that I think is fully resolved. So I'm a bit careful in that. But yes, I would imagine that this is not good. Macroscopically, at macroscopic times in experiments where, of course, they use real membranes that are much more complicated. At macroscopic times, you see non-Gaussian displacement distributions. In this case, it's almost exponential. That's a paper from a few years back. And they clearly see anomalous diffusion, mobile versus immobile particles. So it's really there, and you can measure it when the system becomes normal. This one. Now, how are we doing in time? I probably run over time already.
Yeah, it's 20 minutes to the hour. You can just have 10 minutes to start wrapping up. So yeah.
We need a second. Anyway, so I showed you this diffusing diffusivity model. Now let's apply it to our fractional Brownian motion. So again, we have our fractional Gaussian noise here, and now we have this modulation by the stochastic diffusivity. And when we look at that, of course, we can, in this model, it's not exactly solvable. We don't have analytical solutions. We only get the long and short time behaviors. And now we see that depending on the details of how we phrase the model, we get very different behavior. And this is bad news, of course, from a modeling point of view. So in one formulation, you see whether you have superdiffusion or subdiffusion, it crosses over to normal diffusion. In other examples, superdiffusion stays superdiffusion, subdiffusion relaxes to normal. And the reason actually why subdiffusion is more fickle than superdiffusion is for subdiffusion to work in this fractional Brownian motion, the area under your correlation function is exactly 0. You have a negative part, you have a positive part, and it adds up to 0. Once you destroy this, I don't have a more physical argument, but once you destroy this property, you relax back to normal diffusion. And that's what happens here. And you also see that effective diffusion coefficients have very different behavior. The only thing that's stable here is the crossover from exponential to Gauss. So this is not any finished work, it's an observation. We need to understand better what's going on here. And also, what is actually the appropriate model for a given observation. So that's the third case. We also looked at some other quantities, let's forget. Confinement. We have correlated process. So you have a wall here, and you have one, let's say, a positively correlated process. So you have the particle here. The next jump will take it across the boundary. So we use kind of a reflection method. And the details of the reflection don't matter. They only matter very close to the boundary. So what I say is independent of the implementation. But the one step that will take it across will always be followed by a step in the same direction. That's the correlation. So this is why these particles try to accumulate next to the boundary. And this is what you see here. This is a super diffusive fractional.
Sorry, but depends how you model it, no? Because if you actually say that you try to come out and you come back, you're coming from the left now.
It's still the same direction the particle will want to move.
But if I think about just the correlated angle,
No,
okay, so then you
Just
just
the
come back.
reflection only, look, the reflection only changes the position of the particle. It doesn't change its sense of direction. Don't think of a massive, for a massive particle, this is very different. When it bounces back, yes, then you have a velocity. We are talking here about an overdamped particle. Think of realization. You have a polymer, and you look at the motion of this one guy in there. And the whole polymer doesn't feel the boundary, only that one part. That would be a potential simulation realization. So the whole polymer is moving towards the wall. And then this particle is colliding with the boundary. So it's put back a little in the simulations, but the whole thing is still moving towards the boundary. Okay.
Yeah, I mean, okay, it's a way to model it in a sense. Yeah,
Yes,
okay,
but this
okay,
is essentially what we see here. And you see that in these simulations, I mean, the simulation doesn't know anything about it. You have your Langevin equation and you have your boundary, and you see how this guy is gluing to the boundary. That's also what you know from active systems, right? When they have all these bacteria, whatever moving, they always try and actually build up a non-equilibrium pressure on the walls. For subdiffusion, exactly the opposite. The particle avoids the walls, and this is Brownian motion. And you see that when we look at the stationary probability density, this is, of course, what we know. This is the equilibrium case. This is subdiffusion. You see that you have a depletion next to the boundaries, and here you have an accumulation for the superdiffusion. And if you don't believe our implementation of the boundary condition, let's go to a potential. So instead of having a wall, we have a steep potential. For a Gaussian potential, it always stays a Gaussian process, but when you have, let's say, an x to the 4 potential, this is what happens. This is for the superdiffusive process, you get the same behavior. So this is why I feel on a safe side in all these claims. Here, this is innocent, this is just introducing a force in biological equation. Okay. Oh, we talk about this afterwards. Good. We apply this. This is very phenomenological, but it's beautiful collaboration with biologists in Santa Barbara, Schematis Janushonis, and they look at the densities of brain fibers, serotonergic axons. It's a beautiful word, I always need to read it off. And they see a very strong increase in the density close to the skull of the mouse, where you have boundaries. And we try to model this. You know that a typical model, an innocent model for a polymer is a Gaussian chain approach. And here we introduce these correlations. Other people are working with this as model polymers as well. And you see these are kind of the polymers we create with this fractional Brownian motion, and these are measured trajectories. I mean, it's not too bad. And what we can reproduce with this model is exactly these accumulations next to the walls, exactly the same effect. This is for Brownian motion. You see equidistribution, beautiful. Subdiffusion has these depletion zones, but this seems to be very nice. And for people in biology, they have at least some kind of a model that they can now use to reproduce very complicated shapes that they measure. For instance, we also did, I don't have an image here, we also have three-dimensional resolution. And for me, as a theoretical physicist, it was great. I came there, I was holding the human brain. I mean, this is, something, it's an adventure. Okay, I will not elaborate. This is all stuff that I want to quick. Oh yes, one final remark on this non-Gaussianity. So I have a collaboration with a local colleague in Potsdam with Karsten data, and we have two sets of experiments that have a very strange behavior. So before I showed you, we have systems, they're non-Gaussian, there's correlation time, and it crosses over to non-Gaussian, it crosses over to Gaussian. Here they have a system that seems to converge to an exponential shape. It's not that surprising if you want to think. I mean, they're looking at individual cells. Individual cells have breakfast at different time or whatnot. So they can't be all the same. But the fact that we have now two very different systems, very different experimental realizations, and we see this convergence to exponential, it's something I think is deeper and definitely something we try to find out more about. And actually, I found in literature, finance literature, that there's something like a Laplace motion. So this is a downsampled Brownian motion that's sampled or subordinated to a gamma distribution. And then this produces you asymptotically an exponential distribution. There's also a fractional Brownian motion extension, then it's called fractional Laplace motion, that's invented by Mark Metzler, and this is something we try to explore. Let me skip this over. If you give me 3 minutes, 3.5. I want to make one point about data analysis, because that's another field that we're working on. And of course, I didn't tell you in enough detail. Anomalous diffusion, we kill one of the requirements or more to get normal Gaussian Brownian motion. Right? We have all these conditions that will get large. If you violate some of them, you will get anomalous diffusion, non-Gaussian. But you can violate them in many different ways. You can violate them with these diverging waiting times that I introduced at the very beginning. You can violate them by the correlations. There's other ways to violate them. So when we have data, as a physicist, we want to know what is kind of the cause for the anomalies that we observe. And now you can, of course, go with traditional statistical observables. You have a single trajectory. You ask, for instance, is it ergodic or not, correlations, whatnot, and then you can have a decision tree to at least narrow down with a certain confidence what you're seeing. Actually, Yasmin was the student who worked on this here at another program. We, apart from inventing a lot of observables, complementary observables that we use, we also work on Bayesian data analysis, which gives us certain confidences for models. I mean, here we see for given data set different kinds of models, and we also use it to extract estimates for the parameters. However, what you see when you let different approaches compete, it's machine learning that wins out. I mean, that's the typical standard that machine learning wins. So we organized 2 years ago with some friends in Spain, we organized the anomalous diffusion challenge. We put simulated data out on the net, and then groups could analyze the data and send in their results. It's this diffusion coefficient, anomalous diffusion exponent, whatever, and it's this model. And this was then summarized in this paper. And now we're preparing the next anomalous diffusion challenge, which is much more challenging, of course, because now we put video images. Then you also need to extract the data first with all the noise involved. So, and machine learning were the winners. I mean, our Bayesian stuff, we were, I think, the second to last. For us, but they have the advantage. Training a machine is very simple. But for the Bayesian analysis, we need all the likelihoods. We need to calculate all the different models. And we were simply not done with all of them that were relevant for the challenge. So the other thing, and that's my last point, is of course the danger of machine learning. It's so easy. You always get a result, right? Whether it makes sense or not. So a very simple example, this is work with my PhD student Henrik. Let's say you have a long time series and you run it through the machine and you get the output, okay, this Brownian motion, nice. But when you have a short one or bad statistics or whatnot, the result can also be alpha is one Brownian motion. But you know, when you look at you let it run through an ensemble of machines, the same time series, you could actually see a distribution of alpha like this, very broad. So the information, the output of the machine is nonsensical. So we tried at least, this is the first step, and of course we need to work more, but we tried to get a grip on this. So we have this, these machines, we train the machines, we have an ensemble, and then we apply this to data, and then we have, for instance, here as a function of the anomalous diffusion exponent, you see the likelihoods for a given output. So if you get a given output and it's here, Henrik used a very deceiving color notation. So I can't see the difference between the bottom and the top color. So don't ask me which is what. So if you're up here, you can be sure, okay, with a quite good confidence, this is actually the reality of what the data show. You have other cases, you know, when it's very difficult to tell when the likelihoods become very similar. So at least we have a handle now of classifying how good is the output. And we can use it for mixtures of models. So here we have two models and we have a mixing factor, and how good can we distinguish them? And of course, once you get close to normal diffusion, it always is the worst result, because all those models converge to the same behavior for when you have the alpha equals 1 exponent. We also use it for change point analysis, so we get very clear changes. For instance, here, what did I have? That's the alpha value that is changing. And then I also want to say machine learning, brute force, neural network approach is not always the best. I have a Polish friend, Janusz Żwabiński. He took part in this anomalous diffusion challenge. Computers crashed, so he had to do the whole challenge on his lab. So he couldn't do machine learning, it was way too computationally expensive. So he went back to a feature-based analysis. So he analyzed features of the data and then fed the results of the features into a routine. And it's I don't know, I forgot the numbers, it's maybe 1% of the computational effort. And his feature-based method now is almost as good as the best machine in this challenge. So, you know, sometimes a bit of the gray matter up here helps as well. So it's not necessarily the brute force that always good. I will not go through the summary here. You can, I think, download the talk from the net anyway. I'm here until end of next week, and I will be back later in August, so I'll be happy to discuss after discussion. Thank you.
So for the question, we should write to you, no? So we don't ask nothing.
Oh, hi. Both is appreciated.
Do you have any comments or questions?
Yeah, when you showed the mouse playing with the protein accumulating at the borders, it made me think of that one. It made me think of coffee stains in paper. There be a relation in the processes that go on?
Well, the coffee stains, they emerge from instabilities. You don't have a hard boundary there. There's a very different, very different kind of effect. But when you look at it, it looks exactly like this. Yes, it's not clear what happens there. I mean, they just developed a technique by which they can actually see these fibers grow. So far, people don't know whether they grow more or less in parallel, whether they have one pilot fiber and the others follow. And of course, now we're adding branching, because that's the natural process. It includes branching and maturation.
There is a third dimension.
We do it in 3 dimensions now. Yes. Fortunately, my colleague Thomas Feuter has extremely big computers in Missouri Roller, because fractional Brownian motion is very, very expensive to simulate. Yes. Thomas, you
I
know.
want to ask a simple question. Yeah.
Yes,
So you mentioned a few times Brownian, but not Gaussian.
yes, yes.
Actually, what do you mean by this? Maybe you can explain this.
Yes, this is or Fickian non-Gaussian. So it means that the mean square displacement has a linear scaling in time, but your displacement distribution is non-Gaussian.
Oh, I see.
It's kind of a brand name that was established by experimentalists. It was actually, you have similar phenomena. I mean, when I talk about these kind of super statistic or diffusivities, it's techniques that I also afterwards learned that were already used in modeling of turbulence many years ago. You have similar features in glassy materials. I mean, Walter Kolb, for instance, is using these approaches, but people always use different names, and then you can't find it in literature. I mean, here we need some artificial intelligence to help us, because also this Laplace notion, I have never heard about this, albeit, my Polish friends have a paper on this, but I never heard about it. And I found it through a Wikipedia page when I was looking for exponential distributions, right? This is still bad, we're doing still bad in that's it.
Yeah, I mean, I have a couple of questions. The first one is related. I mean, you show at some part, I mean, that if this system was crowded, something was happening and different behavior. So what I'm trying to say is that at some point you can have anomalous diffusion induced by interaction with other particles. So it's a collective effect.
Yes.
Then you may observe that you are looking at one single particle.
Yes.
I mean, trajectories, and you may come up. I mean, you may try to get a model which ignores basically what happens with the environment. So something that could be eventually linear in the probability, so that you don't need to go linear pocket find or something like that. And that the question is, that model exists or not? That it may be matter of coming with a good model.
Yes.
And when you can do that, basically. Because this is kind of in one case we are looking at the many bug effect, trying to reduce it to one single particle kind of model. And of course, in that model, you can get anomalous behavior because in fact you are ignoring what is happening.
No, you don't fully ignore it. So yes, for a complicated system, we're typically lost, right? I mean, we have a very simple mind. We come with very specific processes. But for instance, these anti-correlations, they can be understood in terms of many particle interactions. So already when you have the Langevin equation for position and momentum of a harmonic oscillator driven by noise, and you integrate out the momentum, you will have an exponential memory in the equation for the position. And what happens in these more complicated systems like this model polymerization, so you can write it down by coupled simple Langevin equations, but then you integrate out all the other degrees of freedom. In that case, you can do it exactly. And it's analogous to Nakajima 20 in quantum mechanics. So you integrate out all these degrees of freedom, and they actually affect that. In that case, the memory consists of individual exponential contributions, but the amplitudes and timescales, they scale, and essentially they build up a power law envelope. So you have a many particle picture, you integrate out all the other particles, and then you get this effective one particle motion. That's more complicated.
Yeah, but suppose I think I'm getting what you're saying, that I think I can do. But suppose that you have a system that is phase separated. So you have a dense phase and a diluted phase. Now the particle may enter into the high density region.
Yes.
So the process is in fact relaxing. So if I can look at the entire picture, I may come with the conclusion that my particle may be subdiffusive, while in fact I'm looking at the transient and the system is phase separating, and then I'm looking at, single particle will do.
Of course, I don't say that we can, beat everything with really simple approaches. So, for instance, I mean, people, not only us, we're trying to understand, for instance, what happens when your environment is changing, right? This also happens for financial systems. When you know you're getting close to instabilities or whatever, then this roughness stuff is changing. So at one point we have, of course, some input that we need to bring, albeit we will not understand, you know, microscopic physics. I agree. I mean, this is still on the stochastic level. It's some coarse grading that happens.
But can you run a test to say, no, I can go with this kind of approach, and here there's a warning that you will not do
Yes,
it.
this is exactly what we try to do by looking at all kinds of different quantities. So here I only showed moments, I showed correlations. We can also have a lot of other quantities to look at, and then at least close it down to specific kind of physical interactions. They're effective sometimes, yes, but a very prominent one is this viscoelastic stuff. And there, of course, you don't have springs between the particles, but when you have very fluffy particles, they come close together. You have an entropic repulsion that acts like a harmonic spring. So at least this viscoelastic stuff we can sort of understand. But of course, when you want to go deeper, and you look at interactions and whatever, it gets intractable on such a level. Okay. Yes.
Thanks for this very interesting overview of so many different systems.
So many
that you work on. Yeah. So regarding these results, I would say that super diffusion results should be expected whenever the space is confined and much smaller than the natural scale, the characteristic scale of movement of the object. You see that in mice in experimental arena, which they would go in nature, like along hundreds of meters, kilometers,
Yes.
and here they're confined to 2 meters. Or fish in aquarium, or even in the nature, you see that in small ponds. That I think it's the simplest explanation. There are, of course, other explanations of risk prediction and things like that. But I'm surprised to see the subdiffusion more than, because I think the neurons are confined by the brain. You know, metaphorically, we can think much more than this box. But how you get this subdiffusion?
No. Here it's really a super diffusive model. Here, this is just model simulations. This is the real thing, and this is replicated by super diffusive growth of the protein of the fibers. So essentially, they have a persistence. They tend to go in the same direction, and that's what's causing this accumulation at the back. But actually, now I have a chance to look at the previous slide, which is fun. Where is it? Where is my slide? Here. So let's look at a Langevin equation where we have our fractional Gaussian noise, and now we have a confining potential. I showed you steep potentials. This is an example what happens when you have an x to the 4 potential, where you have a shallow potential. For instance, it could be, you know, a potential keeping you in a habit. If it's too negative, then the particles can escape. Super diffusive particles can then, you know, they will not have a stationary solution. There's no Boltzmann, but they overcome the confinement and they can go to infinity. The funniest thing. And there's a critical exponent for that. And it's similar to what Levy flights actually. They have the same property and the same critical exponent. That's a funny thing. You know, with confinement, it's not enough. So you need a bit more confinement. Yes.
Maybe it's a good question. But you have any negative correlation, the noise can be complex number.
No, there's nothing complex. Or I didn't get the question.
Well, I mean, when you have correlations, negative correlations, the noise for tau goes to zero.
It's never complex.
No, it's not complex. Of course, you have a little delta leak when you extend it. So when I show this power law scaling, this is strictly for tau unequal zero. But yes, you can regularize it. You can put the delta function in. So it works because I mean the correlator always needs to be on. Okay, now forget about what I said. Yes, it's real, no complexity. Yes.
So can also another question. Can you already update how is this topic in turbulence?
So in turbulence, people, I'm not an expert, far from, but in turbulence, people use combinations, superpositions of many different diffusivities. And then they have different laws for how these diffusivities are distributed. And then they calculate transport quantities. So this is what Christian Beck called superstatistics. So they have kind of a Brownian particle, but then on top of that statistic, they put a distribution of diffusivities. And then they could reproduce some of their observations. There's again a phenomenological approach, but at least it gave some understanding. And there was a lot from the Russian school, I think back in the 70s or something, 60s. But I can tell you about the literature.
Oh, one more question.
Can I? Well, perhaps it's not related, but I'm coming back again to the mouse.
Yes.
It's really fascinating.
Yeah.
I shouldn't have said I was touching the radio.
I don't think that would be the case for this model exactly that you've shown, because it's more appropriate what actually you were doing. But just this type of the simulation result, which you see with the simulation of the boundary, in other systems, I know that you can get the similar type of profile when you have non-local reactions. So when you have just a simple reaction diffusion, for example,
Sure.
no, but well, here you don't have reactions, right? But if you allow those reactions to be non-local, you're going to have the effect in the boundary, which could be of different size.
Absolutely.
So that's, well, just in different system that perhaps wouldn't be the only explanation of why you see this type of.
Look, I mean, I can't even rule it out completely because we don't know at this stage, or biologists don't know what makes them grow in a specific direction. It could be guided by an underlying chemical field.
Also, because
Definitely.
those for sure can interact non-locally because they, well, by the nature, but.
No, there's a lot of open questions, but it was a fun project. I loved
Yeah,
it. People jump on it, obviously.
I like the flower.
Yes.
Okay, let's thanks, now.